Hello, Engineering Glass. This is Electricity 101. Now, this might be a little bit of a hard topic. I know a lot of people have tried to understand engineering, specifically electricity, and electricity can be really, really hard because it's a little bit different than mechanical and civil engineering or any type of subject like botany or studying animals or anything because you can actually see the animals. Electricity you can't see. So, how would you actually go about studying it? Over here, we have a little aid. We have something we call an analogy, and we're going to compare electricity to water. So, actually, through this example, you'll see that there are a lot of similarities between electricity and water. Over here, we have just a water faucet. We have a brick wall with the red bricks. I hope you like it. So, sometimes you have a water faucet outside and you have a hose attached to it, like a water hose, and you might use the water hose for doing something like, let's say, washing the deck, right? You're trying to make something really clean by applying a lot of pressure. So we can call this water in the hose just these little balls. We can represent it as balls instead of just this one big mass of water, just to make it easier to see. And we have our water hose, as you can see, and our water hose would be analogous to our electrical line or a wire, and the charges in electricity would be analogous to the actual water balls that we have in those 12 little dots within that water hose. Now, going back to some really electrical engineering principles, we have a thing called Ohm's law. Ohm's law says that voltage equals to current times resistance. And I know you're thinking current, where'd you get the I from? I'm sorry, I really don't know, but that's the way it's written. V equals to IR, voltage equals to current times resistance. And we also have power. Power is given in watts, and this might be a little confusing, so you might want to write it down when you study this, but power is equal to I squared times R. Power equals to I times R. So it's just like voltage, except that it's to an extra magnitude. So now, just to give a good overview of what we're doing here, we have these 12-rod balls coming out this water hose. But that's not the current. The current would actually be the flow, or the amount of water balls you get out per a second. So, of course, it's the flow of all these water balls that come out. Now, not all water hoses would be the same, right? So not all wires will be the same, even if you have the same amount of current. You might still get a different effect. But how would you get a different effect? Just imagine a water hose. Imagine if you put your thumb at the edge of that water hose. What's going to happen? You might get more pressure, right? It's like pressure washing. You'll have more power and you'll be more effective in washing things. It's not just going to drip out anymore. It's going to spit out. It's going to burst out. So that's equivalent to our power or our voltage. So as we see here, why is that so? When we put our thumb on the edge of that water hose, we increase the resistance. Now we have high resistance, and if we were to let go and we were just to have it to where it's just pouring out the regular water hose, no kind of end on it, no kind of cap on it, that would be called low resistance, and that has low power. So what that means is that not as much work is getting done. So this is the equivalent, or this is the analogy between water and power. So whenever you see something like high power devices or high power lines, that means that there's usually a lot of current, or it could be resistance, but there's a lot. You can kind of think of it as like a water hose. It's spitting out a lot of power in there. So now we can rewrite this, as I said before, P equals to I squared R, or power equals to current squared times resistance. And the way we can kind of write this to sum it up is resistance goes up. If the current stays the same, if the resistance goes up, the power goes up. And if the current stays the same, or the flow stays the same, if the resistance goes down, the power goes down. So now we have a pretty good summarization of what electricity is. Now, next time you see something like the current, you'll know it relates to how much is flowing, but it doesn't necessarily mean high power. That's something very, very important to realize. It's all a balancing act between multiple factors. One thing I will touch on here briefly before we go is that in mechanical systems, we have power equals to velocity times force. So why don't we use the same thing for electricity? It's kind of funny. It's a long story, but the thing is, just like all these symbols, like I equals current, don't really make any sense. At one time, we did actually call voltage electromotive force. But then, in order to honor Alexander Volta, we called it voltage. But it's essentially the same thing. Mechanical systems, electrical systems, P equals the velocity or the flow. In our case, it's 12 water balls per second times the electromagnetic force, or current times the voltage, equals the power. And there we have it. That is electricity. Thank you. Bye. Hello, Engineering Glass.